So today we want to talk about solving oblique triangles. And an oblique triangle is just a non-right triangle. No 90-degree angle. So far, all our solving triangles has been for right triangles, right? We just use right triangle trigonometry. And I should say that this lecture and next is not going to teach you to solve anything you couldn't already solve with right triangles. This is really just a technique to make it easier. We can already solve these with right triangle trigonometry. Here's an example. We're not going to do this. I just want to show you what's involved and motivate this. Here's a non-right triangle, right? And suppose I'm given that this is 140 degrees, and this is 5, and this is 7. And I say solve this triangle, meaning find all the other angles and sides. How can I solve this? Well, it's a mess, right? It's not a right triangle. What do? You can drop a perpendicular, for instance. Suppose I drop a perpendicular here and make a right triangle. And now I can solve this, but it's kind of a mess because now I need to call this alpha and this beta. And I can say, well, alpha plus beta equals 90 degrees, equals 140 degrees. Now what's more, if I call this side h, then cosine of alpha is h over 5. And the cosine of beta is h over 7. Oh, look, I've got 3 equations and 3 unknowns, h alpha beta. I can solve this, but what a mess. And it's hard. That's the hard way to do it. We don't want to do that. We want an easier way. So let's find easier method. And the easier method is to use one of 2 laws, the law of sines or the law of cosines. And the idea in this method to solve oblique triangles is to do this. One, if you're given either angle followed by side, rotating in order around the triangle. Remember that from geometry? That was a congruence theorem. If you had a triangle with, where you knew one angle measure, the next angle measure, and then the next side measure, there was only one triangle that had those measures, right? You could turn it around the plane, flip it upside down, but it described a unique triangle, the same, it had all 6 measures, angles, and sides the same. Only one triangle. So given that data, I can try and solve the triangle, find out what are the other 3, the other angle and the other 2 sides. Or I might be given angle, side, angle data. That's a congruence theorem in geometry, right? There's only one triangle that has a certain angle followed by a side followed by an angle. Or we could do side, side, angle. That was not a congruence theorem, unfortunately. I'll put a little asterisk here. This is a bad case. But you could still almost solve the triangle. Sometimes there was no solution, sometimes there was one solution, and sometimes there was 2. But you could figure out what the 2 were, maybe, just approximately. In this class, we're going to find out exactly what the other 3 measures are given those 3. But given one of those three cases, we can solve using the so-called law of sines, which I'm going to put up shortly. Somebody gives you three measures of a triangle consisting of angle followed by side, angle followed by side, followed by angle, or side, side, angle. You can solve that triangle or find the different cases in the last situation there. On the other hand, if instead you're given side, angle, side measure, that's also congruence theorem. And side, side, side is also congruence theorem from Euclidean geometry. These are not so easy to solve with the law of sines. It turns out to give you multiple equations and multiple unknowns, and it's kind of a mess. Maybe it was just as well drop the perpendicular, right? But given these, there's another law called the law of cosines that makes it really easy. That'll not be today. That'll be next time. Okay. And then finally, what else can we get? Angle, angle, angle only says that two triangles are similar, right? You can have a triangle like this and a triangle the same shape with the same angles that's bigger, any size whatsoever. You can't solve for the sides at all with that. So you simply say, this is really only two pieces of information. Once I know the two angles, the third one has to add up to, make these add up to 180, so it's already determined. Doesn't determine the triangle. The idea is if I'm given three pieces of information other than angle, 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 I can solve the triangle by one of these two laws. The law of sines or the law of cosines. So that's where we're heading over this lecture next, is to solve every oblique triangle simply instead of dropping perpendiculars, using either the law of sines or the law of cosines whenever we're given three independent measures. This one not being independent measures. That makes sense? I always think if you build one of those models or glue one of those models together, model car, model ship or airplane or something, it always helps to look at the box first and see where you're going, right? You try and put those little pieces together without looking at the box, it's terrible. Once you see the picture, right, hopefully it's a lot easier. That's the purpose of this, show you where we're going. We're going to be able to solve any non-right triangle in simple fashion by using the law of sines in these three cases or the law of cosines in the other two cases. And angle, angle, angle doesn't give us a result. What happened to this board? I think they claimed it was the wrong thing. So here's the law of sines. We'll give it as a theorem. It's real simple. Love the simplicity of mathematics to tell you big things sometimes. In any triangle whatsoever, where you mark the sides and angles this way, so I'll draw it, doesn't have to be a right triangle. And by the way, these all work for right triangles too, but we don't use these for right triangles because the same methods we did before are easier, they're shorter. This will be longer, but you could use it if you wanted, right? In any triangle, suppose we label these sides A, B, C. There's no longer a hypotenuse and legs because it's not a right triangle, right? So you put A, B, and C wherever you want, right? But what you have to do now is opposite side A, you put angle alpha. Opposite side B, you put angle beta. And opposite C, you put gamma. Gamma isn't actually the third letter in the Greek alphabet, but they still use it for some reason. So alpha, beta, gamma. We'll put on those corners. And labeled that way, it turns out that always the sign of alpha is to its opposite side A. The sign of beta is to its opposite side B. as the sine of gamma, its opposite side C. We'll call that equation 1, the law of sines. And actually, it's 3 equations, if you think about it, right? This is an equation, sine alpha over A equals sine beta over B. If you drop this one out, this is an equation. And if you drop this one out, this is an equation. So it's 3 equations in one. Just relabeling the sides, however, makes them the same equation. So it's only 3 equations. It's 1 equation with the sides relabeled, really. Now the idea is we can use this to solve triangles in those 3 cases. Here's a real classic example I think is really fun. Let's see if I can screen on this one. Got it. So this is the Leaning Tower of Pisa. And maybe you ask, I wonder how far it's leaning over, right? A good question. They built it on shaky ground, or not rock, but on weak ground when they first built it. And it started quickly to lean over. And over the years, it got leaning so far that it became dangerous, and they tried to straighten it up, but they didn't actually straighten it up all the way because then nobody would come to see it anymore, I guess. So they left it leaning a little where it was still safe, but not straight up in tradition. But, you know, it wasn't originally intended to be tilted. It's just began to lean because of the ground underneath. Suppose we want to find out how far it's leaning. What is this angle at which it tilts over? Well, if we draw this triangle here, we can figure it out because we get this angle here and then subtract from 90 to get how far it's leaning from straight up, right? So let's see. Suppose we know from the building specifications that this thing is actually 56 meters tall. And we go out here and pace off from here 25 meters, and then we take a sextant or a protractor or something and measure 73 degrees here up to the top. We can actually figure out with those 3 pieces of information to solve the whole triangle using the law of sines. This is, after all, if you look at it, a side followed by a side followed by an angle. The third case, for which the law of sines makes this easier to solve than dropping perpendiculars or something like that. So let's try the law of sines for this problem. Let me take it off screen. Go. So here's Leaning Tower. This measure, 56 meters, roughly anyway. I don't know what's the exact specification. 25 meters, I pace off at 73 degrees. Side, followed by side, followed by angle. Tells me I ought to use the law of sines. The law of cosines and the law of sines actually both apply to any triangle, but what happens is if you use the law of cosines for this, you won't be able to, you'll have to get multiple equations and multiple unknowns. It doesn't make an easy problem. But the law of sines does make an easy equation. So law of sines in the side-side angle case. What do I put? I want to put the 3 pieces of information I know and 1 I don't know into one of these 3 equations up here. By having 1 unknown, I can solve for that one, right? Just like when we solved right triangles, we'd try and put 2 pieces of information and 1 we didn't know, so we could solve for the 3rd. Now we're going to put in the 3 things we know and 1 we don't know. So I can label these however I want. I could call this A, and then this has to be alpha opposite it. This one could be B. Right? And then this would be beta. That leaves this for side C and its opposite angle gamma. So what we want to find here is actually this angle, 90 degrees minus gamma. And I should say that in this section, all our measures are going to be in degrees, with the idea that this kind of rule you usually use when you're out in the field somewhere and nothing is at an exact nice angle. Otherwise, you'd have right triangles or something, right? You're a surveyor or an architect or something like that, trying to design things at all sorts of odd angles out in the field, measuring mountains or something, a geologist, geographer. So in that case, when you're measuring things, degrees are easier to work with, right? Because 90 degrees makes a right angle and all that. You can kind of imagine your head. Let's see what we get here. I have this side and this opposite angle. I could use those. So I could say by equation 1, the law of sines, sine of 73 degrees is to its opposite side 56, as this one is at its opposite side. Sine beta is to 25. So there's the law of sines with 3 numbers I know put in and 1 number that I don't. Right? I can solve for it. I just multiply both sides by 25 and say equivalently 25 sine 73 degrees divided by 56 is the sine of beta. And consequently, beta turns out to be the inverse sine of that number. Right? 25 times sine 73 degrees over 56. Now, technically, it turns out there's 2 solutions to this, that 2 angles beta between 0 and 180 degrees that have this sign, but the other one is bigger than 90 degrees. We want the angle that's less than 90 degrees in here, right? Since it's tilted this way, we get it'll be less than 90 degrees. So we'll say beta is the arc sine because sine of beta is this number and we want it to be an acute angle. We just run that in the calculator, right? Let's see, I get inverse sine. You got to make sure it's in degrees mode. 25 times sine 73, close your parenthesis, divided by 56. Gives me 25.27 degrees. So beta is approximately 25 point, well, if I rounded this one to 2 significant digits here, right? Significant digits different than decimal places. You start with the leftmost non-zero digit, just count over 1, 2, 2 significant digits. And also these are all 3 significant digits going in here. When you do multiplications, divisions, and trig functions, you carry at most 2 significant digits, because if this is really supposed to be 24.5 or 25.499 or something, I can make the next digit in here anything I want by changing this digit. Same thing with this one and this one. And so if I write in more digits than this, it's all garbage anyway. It could be any number. So I'll just round it to the same number of digits too that went in of the least significant digits in these 3 numbers that went in. All right. That being the answer is the only thing. So I'll get 25 for that one when I round it off. And the squiggly equals means approximately equals here. You don't have to use that, just put equals if you want. But the idea is I'll round to the same number of digits as those have. All right, now that I have that, what I really wanted was this number here, gamma. That's what I'm trying to solve for. So gamma is 180 degrees less the other 2 angles that I have now. See, 73 degrees, 25 degrees. Well, that makes 98. So I've got 82 degrees left. And now that I have gamma, I notice the tower tilts at 90 minus that number from vertical. approximately 8 degrees. Let's put 8 degrees. Okay. So there's a sort of real world problem when you don't have a right triangle because the building isn't straight up.
So I tried putting that in the calculator.
Oh, I rounded it. That's what I'm saying. I got actually 25.27 something.
No, I mean, I'm getting negative 0.306.
Oh, you're probably in radians. Yeah. So, so in degrees mode. Hopefully it'll come up then. Questions? So as you can see, you can do lots of fun stuff with this. This has lots of neat applications too, right? I mean, if you get people in the earth are not too far apart, you got somebody lost in this big forest over here, right? And they want to be found. You can sometimes get a bearing angle here to the person who's lost and distance. And then have another location where you get some angle and a distance. I'm sorry, not a distance. I'm sorry, you get a bearing to them. Where is the signal coming from? A bearing here. And if you know the distance between these two spotting locations, now you can angle, side, angle to solve the triangle and figure out exactly where they are. Or in World War II, right? You have the airplanes coming in. Here's the German aircraft kind of flying, bomb London or something. What you can put is a forward observer and a rear observer here, right? And they each measure the angle up. So they know this angle here and this angle here. And if I call this whatever, theta, then this one here, alpha is known because it's 180 minus this one. Now you know two angles, and if they know their distance apart, they measured it off, and they measure these two angles, they can solve the triangles and figure exactly the whole triangle, and consequently then, with a little more work, fill out this right triangle and find out how high to shoot flak or whatever at the German bombers coming over to London. Anyway, so the point is, we're going to do this kind of problem later, the surveyor's kind of problem, where you can fill out this triangle and consequently another triangle. But you need to be able to do these oblique triangles to solve these problems. All right. Let me try one off the homework now. This is the very first one. And then when you do the homework, maybe you can see if you have trouble, you can go back and look at this. Suppose alpha is equal to 35 degrees is given. Gamma is 73 degrees. And C is 20. Whatever units, meters, feet, something. And this time I'm going to say, I don't just want the one angle there. I want to solve the triangle, meaning I'm given 3 pieces of information. There's 3 sides and 3 angles, so there's 6 total measures. I'm going to find the other 3. So solve the triangle means find the last 3. First 3. I think it helps you often to draw the triangle, right? So pictures are sometimes worth 1,000 words, just like they say, right? 35 degrees here. Suppose I put that for angle alpha. And then angle gamma somewhere, maybe it's over here. Be a little less than a right angle, so I'll put 73 degrees. So I measure this a little more than a third of a right angle, this most of a right angle. And now I want C, if this is gamma, C has to be opposite 20 over here. This is alpha, so its opposite side is A. And then that leaves AC here. This must be B. And this must be its opposite angle, beta. So I'm given these 3 measures. I need to find A, B, and beta. Right? There's my triangle. The nice thing about drawing this triangle out is you can look at it and see whether you want to use the law of sines or the law of cosines. Right? So I look at here and I say, here's an angle. Let's see. And then the next thing I have is an angle because I don't know this one. And then a side. Oh, it's angle, angle, side. That was one of the cases for the law of sines. To tell you the truth, I think it's hard to remember all these cases, right? It's I had trouble trying to teach this stuff, remembering these things. So I use them all the time. I'll give you this hint that I think is easier. Look at that first summary that I did. if you saw a side, angle, side, and side, 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 that was used the law of cosines, right? Everything else is the law of sines. So if you just remember, these two are cosines, side, angle, side with two sides and angle between, and side, side, side is the law of cosines. Then law of sines because it's not one of these, right? That's one way to do it. The other thing is, even if you don't remember, you can usually just figure out which law applies by pretty much brute force here. When I know two angles, what do I immediately know from what we did before about the law of sines? I know the third one because they add up to 180, right? So in these things, whenever you have two angles, always just immediately find the third one. It's less computation than the law of sines. You're less likely to make a mistake. It's easy too. So it's got everything going for it, right? So whenever you have two angles, immediately just use the sum of angles equals 180 degrees. And that's easier than using any other rule we have. All right, so let's do that for our first step. And the other thing I'm going to put steps 1, 2, 3. We're given three things. We're going to find three things, 1, 2, 3. So we'll say immediately, since I have alpha and gamma, I'll write beta must be 180 less those. 180 minus 35 minus 73. Let's see, that's 108. So that leaves me 72 degrees for the last angle. This is almost an isosceles triangle, right? A triangle with two equal angles. They're not quite equal, 73 and 72, but they're very close. So there's one of the three things I need to find. I didn't even have to do anything more than subtractions. However, now I go to the law of sines, right? Because I'm angle, angle, side, or I could now make it as angle, side, angle now that I have this last measure here too. You can use either one. So on this one, I'll say the law of sines by equation 1 there. What I need is to get three numbers I know and one I don't, just like we did on the leaning tower. So I'll say, well, here is a angle on an opposite side. So I'll say sine 73 degrees is to 20 as, well, let's say I need to find A. So I'll say sine 35 is to A. There it is. So here's an equation with three of the numbers I already know and one I don't know. Now what you can do to solve this is algebra. There's multiple ways to solve this. The two most common are you cross multiply this times this equals this times this. You can do that if you want, or you can say, oh, if these are two equal, then their reciprocals are equal, and you can solve it that way. Let's do reciprocals, but do the way that works for you. I'll say if these two are equal, then the reciprocal of this one, 20 over sine 73, is the reciprocal of this one, A over sine 35. How about like that? And now if I just multiply both sides by sine 35 degrees, I have A, right? So equivalently, 20 sine 35 degrees over the sine of 73 degrees is equal to A. I run that on the calculator. I'll give you a warning here on this too. It's very important you close your parentheses on these trig functions. My old calculator there inserts a parenthesis automatically right here each time I do the sign, right? What happens if I don't close my parentheses? Yeah, on the TI-84 and somehow, at least on this old one, it closes them all at the end like that. And now it's going to take the sine of 35 degrees divided by this and close parentheses on that. It's going to take sine of all this stuff. That's not what you want. So make sure you close your parentheses here on your calculator. It'll open it automatically. Some calculators will put both parentheses. You have to arrow out of here, right? But if you let it close it at the end, it'll close it in the wrong spot sometimes. Why am I getting a wrong number? I can never get the right answers on the homework, right? Well, you can spend a lot of time messing with that because you didn't close your parentheses. So don't be lazy and let it close them for you on these. Also, it double checks you too. If you close all your parentheses, then if you actually put an extra closing up here, it will catch it and say, error, too many parentheses on the right. It doesn't say that message, but it throws an error. Let's try this on here and see if we can get it. And there's good news too, actually, because you say, oh, wait a minute, maybe I should do parentheses here so I can make sure it multiplies before it divides. It actually doesn't matter, right? If whether you do the multiply first and then the divide, or the divide and then the multiply, it'll give you the right answer. So you don't need any parentheses for that. You just need to make sure you close your trig functions there. So A is equal to what if I do the division? 20 times, again, make sure it's in degrees mode. 20 times sine 35 close divided by sine 73 close, and I get 11.995. Now, if I think on the answer here, it says round to the nearest tenth. Yeah, so let's put that on here. Solve this to nearest tenth on everything. Assuming these were exact measures going in. Otherwise, it doesn't make sense. These were not, if these were rounded numbers already, not including tenths, then all the tenths would be garbage over here. So assume these were accurate to at least a tenth. Here's what I'll get, and then I'll round it. What does this round to when I round it to the nearest tenth? Well, that means this digit right here. If since the next one is 5 or greater, I have to round up and call this 12.0. And you write down the 0 to show it's significant. All right, so I've got 1, the angle by the sum of angles theorem, 2, a side by the law of sines, and now 3, I can use the law of sines again to find the last side. I can say, once again, I was given this angle and this side. I'm going to go back and use my original data whenever I can, because maybe I made a mistake in here. I could use this to find the last side, but if I do, and I made a mistake here, I'm going to make a mistake in the next step. So I'm going to try and reduce my risk of making an additional mistake just in case. Sine 73 is to 20. This is the law of sines again. Sine of gamma is to C. Right? And I want to find the last thing here. I don't have B yet, right? I didn't C, I just found A, so I need B. As sine beta is to B will give me 3 knowns and 1 unknown. So sine of beta was sine of 72 is to B. We'll find B for me. All right. So one of the law of sines equations here leaves 3 knowns, 1 unknown. This time, let's do it by cross multiplies. You can do it any way you like. Do what's easy for you. Don't let me make you confused trying to do it a new way for nothing. So I'll take this times this, B times sine 73 degrees equals this times this, 20 sine 72 degrees. It's a common factor. Now I'll divide through by sine 73 degrees. I've got B equals 20 sine 72 degrees over sine 73 degrees. And then you round that off to the nearest tenth, making sure you close your parentheses again, right? Close divided by sine gives me 19.89, blah, blah, blah. Rounds to 19.9. There we go. You can solve a triangle given any 3 pieces of information other than angle, angle, angle. And we have one bad case coming up where there might be more than one solution, actually. Hey, that one look all right? One thing you see out of this is it can be very complicated. Maybe we should put this over. Because this is so complicated, it's easy to make mistakes. So I'm going to recommend on the test that you do this. Let's do a check. And here's the checks I suggest. This really isn't in the book. It's all up to you how you want to check it, right? You can always go through and redo all your calculations, make sure they're right. But how about an easy, quick check? Like if you're worried it's going to rain, what do you do? Put your finger up in the air and see which way the wind is blowing or something. Just something simple to get an idea, you know, whether the cloud's going to be moving this way or that way kind of thing. You can do a real simple check. Is the sum of the angles equal to 180 degrees? It's easy to add, right? Well, I recommend these, but do whichever ones you want. It could be that the errors, you know, they add up to 180 degrees and there's still an error, but usually if you do all these checks, you know, when you make an actual error, it's usually a blunder. There's a big mistake and something doesn't come out right here. So that's one of them. Another one is to say the sum of the two shorter sides of the triangle must be greater than the longest side. All right. For instance, suppose I gave you this triangle here, 3, 5, and 9. How do I know that I made a mistake? These two sum to less than this one, right? A line is the shortest distance between 2 points, right? From geometry. How can this line take longer than going around about like that? 3 plus 5 is 8 is shorter than going in a straight line? Nope, right? So that's what this one is saying, is this line is the shortest distance between 2 points. Now the third one is the largest angle in any triangle has to always be opposite the largest side. Okay. That's true of any triangle. The medium angle has to go opposite the medium side. And the smallest angle has to go opposite the smallest side. I call this the 3 pairs test. But that works for any triangle. So if you make a mistake, usually it's a blunder, and you know this doesn't come out true. You know, that you got a small angle and a large side opposite it, or you know the sum of the sides don't add up right, something like that. So these are real quick, easy checks that you don't have to do a lot of multiplying and running your calculator. You can do all these in your head quickly and just kind of say, does it look like it's probably right? And the other thing you can do is you can just go ahead and make the sketch, just fill in the sides and see if they look good. So here's what I got. It's 72 degrees for beta, 72 degrees. And then let's see, A was, B was 19.9. So take the picture you already made, and then A was 12.0. And now you look at these. Do these angles add up to 180? This one plus this one is 108 plus this one, sure enough, 180. And then I'll say, well, 12 plus 19.9, the two shorter sides is much bigger than 20, so that works. And then let's see, the largest side is 20. It's opposite the bigger angle, 73, right? And the medium side, 19.9, is opposite the medium angle, 72. And the last one follows. You don't have to check that. And so all three work out. Probably my answers are correct. If I made a mistake, I'd probably blunder, make a big mistake somewhere. So there's some advice. I'll give you 100% credit whether you do these checks or not. These are just, you got a little time at the end. Check your answers in an easy way like that. Find your own designer way to check them. Well, that was the angle side triangle. Let's try another one. But really, these sort of amount to just drawing in all the things you found and seeing if it looks right. Suppose I have this, that alpha is 37 degrees. This is number 2, by the way. and beta is 49 degrees. And C is 5. Solve to the nearest hundredth, against assuming these are actually exact so that we round to that many digits. Again, solve means find the rest of the main. All right. Whenever you have two angles, I suggest just find the last one. Gamma must be 180 minus these, right? 180 minus 37 minus 49. Let's see, these are 86, so this leaves 94 for the last angle, right? How easy. I probably didn't make a mistake there. If I would use a lot of signs or some other equation, I would have a harder time finding the angle, right? I'd probably make a mistake. All right, so once I've got that one, now I look at the triangle and I say, let's see, 37 degrees is a little more than a third of a right angle. 49 degrees is a little more than half of a right angle. And C is 5. Where does C go? This is alpha. And this is beta. C, the third letter, goes between these two sides. It's going to go right here. C equals 5. Because opposite alpha has to go A and opposite beta has to go B, C is forced between angles alpha and beta. Now I notice what I have rotating around the triangle this way is angle followed by angle information. So this is angle, side, angle. What does that mean? Again, it's not side, 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 or side, angle, side. I'm going to use law of sines. So I'll take two of these things we know, and look, I now have gamma and its opposite side C, so I can say sine of gamma, 94 degrees, is to C, its opposite side, 5, as I can do either one of these I want, as sine of, let's say, alpha, 37 degrees, is to A, its opposite side. And once you've drawn that in, you actually don't need the A, B, and C. You just say sine of this angle to its opposite side, sine of this angle to its opposite side, sine of this angle to its opposite side. It's kind of nice to have the picture for that reason too. So here I write it again with only one unknown and the other three knowns. By algebra either way, so we do it cross multiply again, it doesn't matter. A times sine 94 equals 5 times sine 37 by cross multiplying. Now I divide by sine 94 and get equivalently A equals 5 sine 94 degrees divided by, oops, what a wrong one, 5 sine 37 degrees divided by sine 94 degrees. Now I make sure to close the parentheses on these when I run the calculator. I can do the multiplication and division either order, it doesn't matter. So 5 sine 37 divided by sine 4, 3.016. Blah, blah, blah. I'm rounding it to the nearest hundredth. That here's tenths, here's hundredths. The next digit is 6, so I'm going to round it up and call this 3.02. Now, I'll tell you what's something going to happen in your homework also. You're going to get 3.02 and the homework's going to have 3.03. Oh, what did I do wrong? What did I do wrong? You know what you did wrong? Probably nothing. Depending on the order that you solve these things in, you can get slightly different rounded answers because the first answer will have a little error in it rounding. Then when you carry it over to the next one, it'll carry that rounding error into the next one, which will change its rounding error. So if you're just off by 1 or 2 digits in the last one here, you're probably right, actually, right? don't worry about it if it's not exact. You probably just did it in a different order than the person did the answers on here. So there's A by the law of sines. I have two pieces of information, this one and this one. I have one more to go, evidently. Step 3, I can use the law of sines again. And once again, I'll try going back to my original data if I can. But I didn't, let's see, I didn't have any opposite angle inside the original. So what I'll do is I'll just go as close as I can. I'll say, like this one, sine 94 is to 5. That's gamma, sine gamma is to C as, and this time I'll do, instead of sine alpha is to A, I'll do sine beta, 49 degrees, is to B, and I can find B. So 3 of the 4 numbers known. Let's do this one by doing reciprocals again. If these two are equal, then the reciprocals are either 5 is to sine 94, as B is to sine 49 degrees. And this leads into an interesting hint for you. Now that we've done enough of these, maybe I can say it. I suggest when you're doing this law of sines like this, that you always have to do the cross multiply or the reciprocals. Instead of starting here, just start right here. I'm going to make this note on the side. The law of sines is equivalently stated by saying A is to sine alpha, as B is to sine beta, C is to sine gamma. You can write it upside down, write the reciprocals. This is also the law of sines. And actually, if you look around in textbooks, you'll see lots of them give the law of sines this way instead. Why would they want to do that? Personal preference. They both are the same. All right. So if you want, instead of starting here, just start here, and then you don't have to use reciprocals or cross multiply anymore. Some of what happens in practice is when you have these angle side and angle side angles, it's easier to use this one first because it avoids this cross multiply or reciprocals. But on the next one, when we do the side angle, it was easier to do the one with the way we memorized it. So it just depends on which one you're solving. One of these will be easier than the other. But so I've just put this up, but you can start here instead of here if you want, right? But A is this, what's it, gamma. C is the sine gamma, as B is the sine beta. Just start there if you want. It doesn't matter. It's all the same law. All right, now that I have this, I don't have to cross multiply anymore. It's multiplied by sine 49 on each side. I've got 5 times sine 49 degrees for sine 94 degrees is equal to B. And I run that on the calculator and get B equals, let's see. Oops. Equals 3.7827, blah, blah, blah. Again, if I'm going to round to 2, to the nearest hundredth, also called 2 decimal places, this is less than 5, so I'm going to just call it 3.78. There we go. And then you can go check this to make sure it seems right. Check. Any questions on that one? Those are the 2 easy cases of the law of sines. Actually, the hard one is yet to come, unfortunately. Angle side, and angle side angle. You have 2 angles. You find the third one by the sum of angles theorem. Then you apply the law of sines twice, and you've got the triangle solved. It's pretty straightforward cookbook kind of thing. Now comes the difficult case, the side angle case. The topic for today. We'll say note, given side length followed by side length followed by angle as you rotate around the triangle either direction. You can get actually any one of 3 cases. You can get this kind of a case where here's B, suppose you're given B, it's this length, and here's A, maybe you're given A is this length, and then you're given this angle opposite A over here, so it's angle alpha. And so this thing, you don't know how long the side is. And this one over here, you don't know what the angle is. You're given this side length, and this angle. Well, what that means is that this side has to stay this length, but it can rotate to any angle. If you take a constant length and rotate it around to any angle, what you get is what? Yeah, a circle, right? The circle is the set of all points at a given distance from a central point called the center. So it's the circle of radius A over here. And if A is too short and alpha too steep, you can't intersect the circle with this line, so there's actually no solution, right? You can't make this sign run into this ray. A half line here is called a ray, no matter how you turn it, and so there's no solution. So that can be the case, right? If somebody gives you the angle too big and a side too short. On the other hand, if you make side A longer than side B, like this, suppose you're given A, B, and alpha again. So you have this length and this length, and this time A is the longer side. It doesn't matter what angle you put here, there's always one solution. So suppose I give this angle here, then there's this triangle is the solution. And that's the only solution because, right, I can make any angle I want here. As I rotate this around to all the different positions, it only intersects this half line, this ray, in one spot, right? It starts inside the circle and travels outside, never to return. And so you have one solution. And there's actually another case of one solution also. If you have this triangle with a shorter side and this one longer, so this is with B less than A, you get one solution all the time. This one is with A greater than B and alpha too large. How large is too large? You have to do the computation. It's not like you can look at it and see. Sometimes you can look at it and have a pretty good idea though. All right, so if B less than A, then you get one solution. And then the other case is you could have A greater than B and alpha just right. And if you have this length here for A and this B and the angle alpha goes out in this direction, ray, it might be that by rotating this thing around, the circle is just tangent to this ray, in which case there's exactly one solution. It's a right triangle. So you get one solution this way. When A is bigger than B, you can get the angle just right from a right triangle, but A less than B. You don't have to memorize all these cases, by the way. I'm just trying to show you that it makes sense. The idea that you do want to memorize, it can have zero solutions, one solution, or two solutions is the last one. So memorize that. It can have 0, 1, or 2 solutions. The cases, it's a little useful to have an idea by sketching, but it's not required. Here's what can happen in the other case is you can have a side B given and a side A here, angle alpha. So here's your ray alpha, A beta, and now get this triangle right here. Right, alpha beta A, alpha B A for side angle. Or if you rotate this thing around in the circle, since it can go any direction, you find actually there's another place where it intersects. You could put A right here and use this triangle. So the red triangle and the black triangle are each a solution. They both have sides A, B, and angle alpha. So there's two solutions, but you won't get three solutions or 10 or 127, right? You'll always get 0, 1, or 2 with this. Right? It's not so bad. But the idea is that the other four cases are all congruence terms. You get exactly one result. You know that from Euclidean geometry. But in this case, that side-side angle is not a congruence term. You can get two triangles with the same side-side angle measures that are different triangles sometimes. Or you can get one, or you can get 0. Let's try doing some of those. This one we could try. This is number 3A. Suppose I had gamma is 113 degrees. B is 10. C is 32. And again, solve the triangle. Again, it behooves you to draw this usually. You don't have to. You can solve it without this, but I think visualization really helps you to catch things. Here's where the visualization helps you the most, because often if you sketch this, you can see which one of these cases it is. You don't have to memorize these, I said, but it does help you a little when you try and draw it. So now this isn't AB alpha, but it's still side-side angle if you draw it. Let's put C right here is 32. And then at 113 degrees, let's see. B is 10. Let's put it here, I guess. A lot shorter. And I close the triangle. Oh, there we go. 113 degrees opposite. That looks about right, right? Maybe there's one triangle in this case. Is there? Well, what you can do is you can imagine that case. You're given 32, 10, and 113, but this side can rotate around anywhere. And so you think if you rotate it around, that really looks like there's just going to be one solution. So again, it's this side is longer than this side. There's exactly one solution. I can only, in other words, this ray is arbitrary, and there's your ray, but I can only intersect it at one point with that circle. So you don't have to be able to draw this, but it looks like there's one solution. This one's pretty clear. Some of these are not, but I'm going to say when I draw this, it really looks like there's one solution. But if you don't draw it, you find it out as you go. That's all that works. So I'm going to use the law of sines, equation 1, because this time I only have one angle. I don't have two angles to immediately write the third one down. I just have to go straight to the law of sines. And you'll find, again, for side-side angle, you can get three pieces of information in and one unknown. All three of those cases, that's why you do them for those cases, is you write an equation with only one unknown. By equation 1, well, let's see, I'm given C and its opposite side gamma, so I'll do that. Sine 113 is to 32. Sine gamma is to C as, well, I'm given B here. B is 10. Sine beta is to 10. There's an equation with the three things I'm given and one unknown. And sure enough, the law of sines is going to solve this for us. Now, this time, see, it's good we wrote the signs on top, because I don't want reciprocals. I'll multiply both sides by 10 and take, say, 10 sine 113 degrees over 32 immediately is equal to the sine of beta. So what is beta going to be? Like in the leaning tower problem, I'd like to say, oh, beta is the arc sine, obviously, right? Maybe is the answer. Right, because it's the side-side angle case. There could be zero solutions. There could be one, there could be two. We just have to figure it out. And what happens is when you try and figure it out, it leads you to a contradiction when there's no solution. So let's try this. There's two cases I want to note here. When you have sine of an angle, it's theta actually instead of beta, equals a number, say y0 or something, there is always two solutions in 180 degrees that could occur in a triangle, right? Every triangle angle is between 0 and 180 degrees. There are two solutions to check between 0 and 180 degrees. One of them, you know, always is the inverse sign, right? If sine beta equals a number between 0 and 1, otherwise there's no solution, right? One solution is beta equals the arc sine. What's the other one? Draw the picture and remind you. Here's y equals y0. And if I take this angle right here, this is the arc sine, right? Coming up to it. But there's another place on the unit circle with the same sign, the same y-coordinate, right? It's right here. Which one is the arc sine? Is it this one or is it this one? The arc sine is a unique angle between plus and minus 90 degrees, so it has to be this one. So one solution is this one, the inverse sine or arc sine. And then this one is what? How about that? What must that angle be? Yeah, pi minus that, or we'll call it, since we're doing degrees, 180 minus it. Yeah, because this angle by symmetry has to be also the arc sine. So this angle that we're interested in must be 180 minus the arc sine. So there are two angles to check. One is the arc sine, and the other one is always 180 less the arc sine. So that's what we're going to do here. This is a side note. That's the derivation. When I have sine beta equals a number, I have to break it up into two cases. Side-side angle has two cases to consider. You may or may not get solutions to both. One is you check beta in this case equals the arc sine of the end number. 10 sine 113 or 32. And then the other one to check is 180 minus that. Beta equals 180 minus the arc sine and sine 113. 2. And so I'll run both in the calculator and see what I get. Let's see, again, making sure it's in degrees on the arc sine times sine 113 closed divided by 32 closed. And I got 16.7. Let's round it to the nearest tenth. Let's see what this said on here actually. Here's tenths. Okay, we'll call it 16.7. Well, the only other possibility then is beta equals 180 less 16.7, which is 163.3. All right. So far, so good. But now what happens? This one has no solution. Why? I've given angle gamma is 113 degrees. This one has to be 163.3 degrees. That's already greater than 180 degrees. There's no solution. So this one's going to have at most one solution. But that's what happens. even if you don't draw the picture and see if you have a good idea, just go through here, and if the sum of angles bigger than 180 degrees, then there is no solution to this case. This case, however, is going to work. And I'll put it into 3 stages again. I've given 3, I'm going to find 3. The first one, you find that angle is the arc sine. And secondly, I now have 2 angles, right? I was given gamma is 113, beta is 16.7. So I'll say alpha is 180 minus those. Let's see, that's 129.7. So I've got 50.3 degrees left, right? Now, finally, in step 3, I want to use 3 pieces of information to find the last side. I've got B and C, I need A. So if I need A, I'll put sine alpha, 50.3, is to A. Oh, you know what's on the bottom? Maybe I should use the law of sines upside down, right? So I'll say A is to sine 50.3. Law of sines upside down equals, let's go back to the original equation, C sine C 32 over sine gamma, sine 113. So this is again by equation 1, our law of sines. Isn't that nice? We only have 1 equation today. But the devil's in the details, right? Trying to do the problems with them. So they're hard problems, but it's only one set of 3 equations, if you like, to memorize. So there we go. Now, if I start with the law of sines upside down, all I have to do is multiply and get A must be 32 sine 50.3 degrees. I should put degrees. Over sine 113. What does that come out to be? Times sine 53 comes out to be 26.7 to the nearest 10. Hopefully that's what's in the back. Again, the answers to a lot of these are in the back. You can check, see if you. All right, but the idea is I actually only have 1 triangle. It's this one. The other one was impossible because the angles add up to more than 180 degrees. Well, let's see if I can deal with the difficult case here, at least get it started before we have to go. Last example is this one. Suppose I make a triangle where I'm given, let's say, A equals 3, B equals 4, and this angle here is 40 degrees. So this is opposite A, it's alpha equals 40 degrees. It's pretty hard to tell how many cases there are. I told you drawing sometimes helps, but boy, it's hard to tell. It looks like it might just make it at 90 degrees and there's 1 triangle, or maybe it's a little less and there's actually 2 triangles. I got this one and this one. I got this one and this one. Or maybe it doesn't quite reach. It's hard to tell. In some of these cases, it's unclear, but we'll just try it anyway. We'll use the law of sines and say by equation 1, since I've given this angle on opposite side, I'll say sine alpha, 40 degrees, is to A3, as here I'm given B, so I'll use sine beta, is to B4. Equivalently, by multiplying by 4, I got 4 sine 40 degrees over 3 is sine beta. I solve for beta 2 different ways, right? I've got 2 cases to consider. Case 1 is that beta is the arc sine. This quantity, 4 sine 40 degrees over 3. But there's a second case possible. Beta is 180 minus that. I'm not even gonna write it down. It's gonna be 180 minus whatever this is. This is inverse sine 4 times sine 40 closed divided by 3 closed 58.98. It's 59.0. When I round it. Degrees. So this one must be 180 minus 59.0. So it's 120.0. If I keep my placeholder, this shows that you have a significant digit here. And now let's see if alpha is 40 and beta is 120, then gamma is 180 minus 120 minus 40 actually is 20 degrees, right? Actually 20.0 if I carry the digit here. So this one actually does work. There are two different triangles that are going to satisfy the side-side angle data that we're given. I should write it side-side angle, the bad case. It's the bad word backwards. And remember which one is the bad case. So gamma is that one over here. Gamma is 180 minus beta that we found 59 minus alpha, which was 40. Let's see, that's 99 here. We've got 81 degrees. So actually, both cases are going to work. We're going to get two different triangles. And so this is 1, 2, 1, 2. And then finally, we can use the law of sines to get the last side. We're missing C, right? So we'll say sine gamma, 81 degrees, is to C. As let's go back to the original triangle. Maybe I made a mistake in here. I'll avoid putting it into this part too. Sine alpha 40 is to A, 3. Again, it would have been better to write this upside down, but we'll say now by algebra, again, taking reciprocals and dividing or cross multiplying or cross multiplying and dividing, whichever it is. I'll say C can be written, you can kind of see it, transfer this over here and multiply by the reciprocal of this. You get 3 sine 81 degrees for sine 40. Or over here, you write sine 20 degrees gamma is to C, as sine alpha is to A, sine 40 is to 3. And again, by algebra here, cross multiplying or taking reciprocals, you got C equals 3 sine 20 degrees over sine 40 degrees. When I'm doing the calculator, I don't have to carry these trailing zeros. I put these in the boxes to show the significant digits. Calculator doesn't care whether I list those or not. I'll just do the computation and then round it. So 3 times sine 20 by sine 40 gives me hopefully 1.6. So here's one triangle. You fill it out with these three numbers. And here's the other one, 3 times sine 81 sine 40. This one, 4.6. All right, so two different triangles solve this. Finish it this way and make a good triangle, or that way. That's it. Try section 8.1, I think it is. 8.1, all the homework problems. Some won't be difficult. We'll probably do a little review next time on the homework supplement. Usual. Thank you so much. What I can do with these, I think.